Welcome to AP Chemistry Prep. This is part two. Last time we left off when we were talking about types of substances. Now, if you're following the summary, which I really strongly encourage you to do, you'll see that our next topic is going to be SI units. So that's what I've got on the board right now. SI units. Now, if unless you can measure something, you really can't understand it. And we'll be using measurements a lot in chemistry. So let's get acquainted with a few of them. Now, this SI stands for System International. And indeed, it is international. Everybody follows these units. This is set up really right after the French Revolution. They wanted things to be rational. They didn't like the arbitrariness of measurements. In fact, the first measurement we're going to deal with is length. And the French Revolution said, we're going to make the measure of a length no longer a yard. In fact, a yard used to be the length from a king's nose to the tip of his thumb. And let's see, that's about right. I'm a good king. Okay. But actually, what they did, it says, okay, we're going to make our system of length, our unit of length, the meter. They spelled it M-E-T-R-E, but we've got E-R. And our system of length is going to be, our unit of length is going to be the meter. When they first set it up, it's supposed to be 1/10 millionth of the distance from the equator to the North Pole, but that was tough to measure. So they made a bar about 39 inches long. That would be a meter. Uh, and they set up a bar that they measured very accurately, that everybody measured things against for hundreds of years. In fact, we have a replica of that bar at the National Institute of Units here in the United States. But now they've changed it to a different standard, which relies on light, wavelengths of light, and how far light travels in a fraction of a second. Now, the official unit is the meter, M, and I'll put that unit out here, just M, lowercase. But you'll never see meters used on an AP chemistry exam. We measure things that are a lot smaller than that. In fact, the unit you're going to see for length in AP chemistry and almost every test will be the NM, the nanometer. And this is a prefix that stands for a number. In this case, a nanometer stands for times 10 to the negative 9, a billionth. So when I say a nanometer, I'm saying 10 to the negative 9 meters, a billionth of a meter. So imagine this just a little bit longer. Usually a meter six divided up into 1,000 lines. Imagine it divided up into 1,000,000 lines and then 1,000th of one of those million lines. That would be a nano, a billionth of this length. And what you're going to find out that we'll be measuring is this light. That 405 stands for 405, whoops, invisible, nanometers. 405 times 10 to the negative 9 meters. Prefixes can always be changed into their numbers. In fact, in most of the problems involving length in AP chemistry, you're going to have to change nanometers into times 10 to the negative 9. 409 nanometers, what does that have to do with this? Well, if you could see this light in terms of waves, and it's made out of waves, a single wave of this light would be 405 billionths of a meter. That's the size of blue light. We measure light in terms of the size of its waves. In fact, if you are smaller than this 405, you can't be seen by light because you're smaller than the waves of light. 605, right there. This laser sends out light with wavelengths that are longer, 605 nanometers. 650 times 10 to the negative 9 meters. So you should be acquainted with scientific notation already and moving decimal points, and I'm going to leave that to you. I'm not going to do that math lesson. But what you should remember is that nano stands for times 10 to the negative 9. You can look it up. They'll have it on the AP equation sheets, but you don't want to have to look up the equation sheets. You want to be able to know that. It's worth knowing. Nano means very, very, very small. And when you're talking about a billionth, that is definitely small. So we have a billionth of a meter, not quite the length from here, but infinitesimal amount. So that's our first unit that we're dealing with. Length. The official unit is meters, but in AP chemistry, you're going to see nanometers, and it'll be dealing with light and the energy of light. And that's an entire unit all by itself. So I'm going to erase that. We've covered our first unit and also prefixes at the same time and what it can be applied to. So not only can we measure lengths of things, but in chemistry, we're going to measure the length of light. Now, the next unit here is the mass. And our official unit of mass is the kilogram, which is sort of strange because kilo is a prefix, it means 1,000. And typically, all of our other units don't have a prefix, but the prefix for mass is the kilogram, 1,000 grams. That's because a gram is really pretty small. Let me show you a gram. I'm going to pick one up. And this little weight right there, I can barely see it with my glasses, is 1 gram. In fact, this is on a special set of weights that are supposed to be very, very exact. So you can see why dealing with a single gram would be a bit messy. So we use 1,000 grams as our unit. But even though this isn't quite AP chemistry, it's physics, but I think it's something you should understand. We're measuring mass. And sometimes people will say weight and mass interchangeably. And very often we'll talk about atomic weight when we should be talking about atomic mass. So what is mass? Well, thanks to Newton, we've got a pretty good definition of what mass is. By the way, this is a little bit less than a kilogram. This is about 2 pounds, which is pretty close to a kilogram. A kilogram is 2.2 pounds. So we're talking here about the official SI unit for mass. But what is it? Well, mass is sort of identified by Isaac Newton, and we'll get back to him a little bit later. I'll have another demonstration for Isaac Newton. And he said anything that has mass has inertia. So if we're talking about mass, let me get my marker here. Matter. Mass has inertia. This light doesn't. This does. Here, we've got a beaker with about 400 grams, 4/10 of a kilogram of mass. Inertia is, hey, it worked. I didn't spill the water. Okay. Let me try one more time. 2 times in a row. It would have been a mess otherwise. If a substance is not moving, if it's at rest, it will stay at rest.
This time. Are you ready, Harry? On the count of 3. 1, 2, 3, now! My goodness, it worked! Harry, it's magic!
This isn't going to move unless you apply a force to it. In this case, the force I had was pulling this paper very quickly. So the force didn't get much chance to be applied. But if I apply the force gradually, you can see it starts to move. And that's the other part of inertia. Okay, this is at rest, and it's going to stay that way unless I apply some force to it. The only way you can get something to move that has mass, not that light moves 300,000 kilometers per second, is to push it, apply a force. In this case, I'm going to apply a Newton of force to this mass, and it's going to move. Oof! Whoa! This mass had to be stopped. It took energy to do that. And I had to stop it too. Otherwise, it would just keep on going. If you have something that's moving, it's going to keep on moving unless something stops it. Either friction or it hits something. In this case, we hit a participant. Be careful when you're in a chem lecture because you may become an inadvertent participant. Okay, so inertia, a object stays, and once it moves, the only way you can get it move is apply energy. It keeps on moving until it's stopped. That's a property of all mass. But what does that have to do with the kilogram? Well, the difficulty of moving a mass increases with the amount of matter in it. So the more matter you got, the more difficult it is to move. This barbell, if I'm going to slide it, is 2 pounds. Okay, this is 4 pounds. Look out, participants. No, I'm not going to toss it. To get it moving, I have to apply more force. And to stop it, you have to apply more force. So the more matter you have, the more mass you have because of that factor. But there's another factor that's very important, and this is why I'm bringing this up right now, is because all matter, this is Isaac Newton, he says any particle that has mass has inertia, but also it exerts gravity. Now that's not just being serious. Gravity is an attraction. It's an attraction. And if you have some mass, you are going to attract things. Newton's law. This is the law of gravity. We're using a lot of math and chemistry. The force of attraction, the force of gravity pulling on things. By the way, gravity only attracts. It never repels unless you're in a science fiction movie. You can't shield gravity. It is there. It applies. And there's no anti-gravity unless you're reading a science fiction story or watching a movie. It doesn't happen. There will always be an attraction if you have two masses. Here, I got 1 kilogram. Here, I got 2 kilograms. Now, if I have them here, there's going to be an attraction between them. This is attracted to the ball, and the ball is attracted to this. Oh, no. Now, the amount follows this equation. You put in the kilogram masses and determine how far apart they are. In this case, 2/10 of a meter. Square, multiply, and then multiply by this. 6.67 times 10 to the negative 11. That's a pretty small number, less than a nano. And as a result, you can find out what is the degree of attraction. Well, the answer is this many pounds. I can have it in newtons, this many newtons, and actually it's this many pounds of attraction. That's about the weight of a half a snowflake. So the attraction between these two is about a half a snowflake worth of attraction. There's another sphere around, and I'm standing on it. It's the Earth. Pretty big sphere for us. And this is its mass. 6 times 10 to the 24 kilograms. 10 to the 24 is a prefix called yada. You don't have to know that, but it's fun to say. Yada kilograms. A lot of kilograms. This is the mass of the Earth. The distance to the center of the Earth, because this always goes from the center of objects. That's another story all by itself. If you put in the distance from this to the center of the Earth, 2 kilograms, the Earth, this distance to the center, and you multiply all this out, you get 9.8 newtons, 2.2 pounds, the equivalent of a kilogram. So the reason lifting this is hard is because the Earth's, well, this has mass and the Earth has mass. And that's the attraction. You can have an equation that explains why things fall. The apple will come up a little bit later again. So therefore, we can measure things by the force of attraction. Gravity is what we use in chemistry to measure the mass of objects, the attraction of Earth to them, its weight. And when I put this on the scale, we'll turn it on, and switch to grams, I get about 900 grams. Let me do this to sort of explain that again. Okay? This is a spring scale, and it gets stretched out by the attraction of gravity. And I can read here, oh yeah, it's about, in this case, if I measure newtons, which is an actual force, I get about, pretty close to 900 newtons, which can be translated into grams. So that's what we're doing here. We're measuring this force. Now, in all of our balances, instead of having a spring, they've got a bar, metal bar, that gets twisted a little bit. And as it gets twisted by this attraction, its electrical conductivity changes, its resistance changes. And we can measure that resistance and translate it into mass, that force. So this, any scale that you use that's digital is measuring that force of attraction because it's twisting a little piece of metal in there. Very, very clever system. And you can imagine the programming that's necessary to do that. In fact, it's called gravimetric analysis when we talk about the weight of things. It's the analysis of gravity's attraction to these masses. Nice name. So if you're doing a chemistry experiment and you're weighing something, finding its mass, like this 100-gram mass, you're doing a gravimetric Earth's attraction analysis. There's a little twist. Let me get my other. Okay, here's my little sheet. We're still talking about mass and kilograms. When I measured this here, its mass was registered as 911 grams. But if I were at the North Pole, at sea level, and I measured this on this same balance, it would have weighed 915 grams. Me and this and everything has a greater attraction, gravimetric attraction, in the Antarctic because the Earth is flattened a bit and you're closer to the center of the Earth. And if I were on the highest mountain in Peru, I would weigh only it would only weigh 906 grams. You have about a 0.5% change. So these scales, this is a very accurate one, won't give you the correct weight unless you take into account the differences of where you are. When you buy an expensive scale where this makes a difference, like this is just a kitchen scale. Nobody cares if it's off by about a gram, whether you're in Peru, here, or in the Arctic. So it's no big deal. But if you're measuring stuff accurately, it is. So most balances that are expensive have a standard mass. This is 100 grams. And you put it on here and you calibrate it. So it's arranged for your distance. In fact, a really expensive valance, one that costs more than $2,000, has a program in it where you tell it where you are and you program your location so that it takes into account the correct attraction of gravity. By the way, those influences in gravity also include the spin of the Earth and the stuff that's underneath you. You can tell if you've got a large reservoir of water or ore or whatever by the differences in gravity. And measuring it accurately. So here we have mass, and we're just going to measure it with scales, and you know the term gravimetric. In chem, we're going to be using grams all the time. But you also will want to be able to use milligrams. So let me erase this and write down AP Chem. When we talk about the attraction of the Earth, the mass of a substance, we'll use grams. Here, I'll write it out. Grams or G. Now, a clever chemistry student will also see mg, which stands for milli. 10 to the negative 3. Oops, let me get that negative 3 in nicely. There we go, 10 to the negative 3. So when I say milligrams, I could say 10 to the negative 3 grams. And I would advise you to use milligrams whenever you're measuring something that's really, really small. I showed you what 1 gram was before. If you look at an aspirin bottle, you'll see that these little tablets are typically 250 milligrams. So a aspirin bottle, which is 250 milligrams, is 250 times 10 to the negative 3, or move the decimal place 3 places, 123.25 grams. 250 thousandths of a gram. That's what milli stands for, thousandth. Medicines really, really have small amounts in them. Let's look at this. This is 75 milligrams, 0.075 grams. But in it, the active ingredient is only 1 milligram of prednisone. And that's enough to have a serious or a noticeable effect on your body because it's a catalyst, a biological catalyst. We'll deal with that later. So milligrams can be very useful. You'll see them all the time, and you should realize that milligrams are a very small unit, thousandth of a gram. And you saw what 1 gram was, hardly anything at all. Sometimes they'll even end up having micrograms, which are millionths of a gram. You won't have to worry about micro in AP Chem. It's not used, but we will be using milli a lot. So that's the other prefix you should remember. Milli times 10 to the negative 3. Nano, you already know. We've talked about that. Nano. And of course, kilo, but again, they never used kilo in terms of grams. We'll be using kilo with some other units. All right. Now, we've covered a couple of units. We've covered length, meters, and of course, nanometers is what you want to remember. We talked about mass and gravimetric attraction and kilograms, grams, and milligrams. Time, well, that's the next in the sequence, and seconds, hours, that's it. That's a short explanation. Current, we're not going to talk about right now. That deals with the movement of electrons, and that's going to be in a much later unit. And we don't have to deal with that now. Now, I'm going to skip temperature right now. That's usually the sequence they have SI units in. And surprisingly, this last SI unit, ignore this for right now, the amount of substance is really the most important one. I saved the best for the last on this list. So, amount of substance, you say, hey, didn't we just cover that with mass? Like, no, let's look at this. We'll find its mass. I'll turn my scale on and have gravity do its thing. 197 grams. 197, of course, if I'm taking data down, I always should write what I'm getting, 197 grams. Okay? Ah, 197 grams. So you say, hey, they're the same. They're the same amount of substance. No, no, because let me unveil the secret here. And here, I got some marbles. So I got a certain amount of marbles. Ball bearing steel marbles. But in here, I'm I'm jam-packed with it. In fact, it's taking the cover off. Marbles. So I've got more marbles here than here. And that's what the amount of substance is. Chemists, yeah, it's interesting how much things are attracted to gravity, but we deal with atoms and substances and what they do. And it's these atoms that do things. It's the atoms of oxygen that you absorb. You don't care how much the oxygen weighs. You want to make sure that you've got 98% saturation of oxygen molecules. So the number of things is more important. And that's what the amount of substance is. It is the number. You count. You don't worry about the attraction. By the way, our 2 kilogram mass would be only 151 grams on the moon. Now, of course, even though it's 151 grams, if you throw this at somebody, they're going to be hit by it just as well as they are here on the Earth. So don't be deceived by gravimetric stuff for inertia. But for us, I'm worried about how many atoms. So it's the number of particles. How many marbles do I have here? How many marbles do I have here? More than here. So, okay. Speaking of marbles, $355 grams. 355 grams. Sure, a chemist will weigh their pills of medicine. But a chemist will need to know how much medicine is really there. Who cares how much it weighs? How many little particles of that medication is getting into your body? I don't care how much it weighs. I just want to know how many are there. So let's take care of that. How many marbles do I have? Okay. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 95 and 96. All right. 96 marbles. So you say, wait a second, chemistry is going to be tough because I got to count a lot of things. Imagine counting atoms. I mean, atoms are really small. I mean, how many atoms are in that? I mean, we'd have to count. Well, here's the trick. 96 marbles is 8 dozen marbles. Now, 8 dozen, that's a simpler number. I mean, 8 dozen, fine. If I counted in 12s, it would have been a lot faster. Well, we have that same effect in terms of molecules. Typically, the number of molecules that we're interested in for a lot of things like elements is 6, so let's get rid of, I'll write it down here, 6.02 times 10 to the 23 particles. Particles. It is 10 to the 23, a huge number. Let's see, a million is 10 to the 6. Million, that's gonna be 10 to the 12. And I mean, billions, nothing compared to this. This is more than all the stars that you can see in the sky. Way more. It's a huge number. When you use scientific notation, when you start getting to higher and higher units, this is one below a yotta, which is the highest number you can get, then this is huge. But we need that number for counting atoms. Now, atoms are really small. So if you want to have enough atoms that you can hold in your hand and see, if you want to have enough atoms so that you can have 100 grams, then you're going to need to count out this many. Now, we don't bother with that number. We don't use 96 marbles. We use 1 mole. This number of particles is 1 mole. If I had 6.02 times 10 to the 3 marbles, it would cover the entire Earth by about a half mile or so. That many. I would have 1 mole of them. So the mole is the chemist's dozen. It tells you the amount of chemical that you have. Let me give you an example. Here's a cube. I'm going to zero this out. I can turn this on so the balance says 0. And I'm going to put on a cube of an element. Carbon, the same stuff that you have in pencils. And that weighs 31 grams. Not much. I think I might have paid $15 for this beautiful cube of carbon. This is impressive. You don't see a cube like this very often. This is a cube of the element tungsten, abbreviated W. It is one of the densest substances known. This is more than twice the density of lead. It's amazing when you lift it. So let me see what this weighs. 317 grams. Like, this has 10 times the weight. This has 10 times the weight of my carbon. So you say, you got a lot more tungsten here. I mean, yeah, I had to pay more for this. It was expensive. So, but, I got a lot more. But that's not really true. To a chemist, this is 2.05 moles. 2 times 6. So that's 12 times 10 to the 23 particles. If I did a marble count, I'd have to count out 12 times 10 to the 23. Thank goodness I don't. This tungsten is only 1.7. 2.5 moles. I have less tungsten. I didn't get, if I had the same number of atoms, I'd have to have a lot more of this tungsten here. I couldn't afford it. So in terms of amounts, this is more. No, it weighs less than this. Chemists are interested in how many, because if I'm having a reaction and carbon atoms are doing something, I'm going to have more carbon atoms doing stuff than tungsten atoms doing things. We're going to be using moles all year. Now, you might say, how did you figure out how many atoms were in here? I'm not going to tell you that right now. That's a secret that we're going to save for chapter 3. We have actually 2 units that are specifically on counting elements, and we'll use those throughout the year. So that's something that you're going to end up learning. Now, one extra thing about before I go on into temperature, and you didn't know about this yet, energy. This is going to work with numbers of atoms and mass. Conservation of mass. Back when taking pictures involved a chemical reaction on a piece of film, and you didn't have enough light, you'd use one of these flash bulbs. And what they are is some magnesium element and some oxygen packed together. 9 grams worth the entire cube. 9 grams. So I have magnesium and oxygen, magnesium atoms and oxygen atoms. In a flash bulb, you put a little bit of electricity in here. Oh, excuse me. Safety glasses. Okay. The magnesium and oxygen burned instantly, and they were changed into a compound called magnesium oxide. Nice chemical reaction, lots of energy, lots of light. 9 grams. That was a pretty dramatic reaction. But the mass didn't change. In a chemical reaction, even though you get all these changes, the mass doesn't change. When we start with a reaction, we had 9 grams. When we were done with the reaction, end of a reaction, I had 9 grams. If you keep track of all the substances in any chemical reaction, the mass doesn't change. The mass at the start is the same as the mass at the end. The atoms undergo all sorts of changes in terms of energy. I still have the same number of magnesium and oxygen atoms. So even though they're combined into magnesium oxide, their numbers haven't changed. Mass of any reaction is conserved. So that's something you want to remember with this. And also the number of atoms is concerned. Now, the number of moles isn't, because particles can combine. Indeed, you can have 2 atoms turn into 1 molecule. So 2 moles of atoms can become 1 molecule. So the number of moles isn't going to be constant, but the number of atoms will always be, and their mass will always be. So let's review. Length, kilometers. Oh, not kilometers, meters and nanometers. Kilometers only if you're traveling quite a distance. Oh, nanometers are wavelengths of light. Mass, grams and milligrams. And amount of substance, moles, and we also have millimoles. And you'll find out more about millimoles later. So, on to our next topic in the next video.